In this second example, we're given f of x, which equals to x cubed minus 2x squared plus 3x minus 6, and again, we're asked to write f of x in factored form as well as solve f of x equals to 0. Well, I'll start by moving the question to the side, like so. Now we can get started. So the polynomial we're dealing with in this case is f of x, which equals to x cubed minus 2x squared plus 3x minus 6. And our first job is to write it in factored form, so I'll just write 1 here. Just as we said in our previous example, to write a polynomial in its factored form, we need to find its zeros, also known as roots. And again, just as in the previous example, we notice that in this case, the leading coefficient is equal to 1. Indeed, there's only one x cubed. Now, when this happens, we can try and find this polynomial's zeros by looking at the factors of the constant term, which in this case is negative 6. Now, the factors of negative 6 are the same as the factors of 6. So those are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And to check whether or not any one of these factors is a zero of this polynomial, we need to proceed by trial and error. So let's go ahead. Let's see if x equals to negative 1 is a zero. In other words, let's calculate f of negative 1. To do that, I use Horner's algorithm, or Horner's method, which I present in a table, something looking like this. At the top of this table, I need to copy the coefficients of f of x, so those are 1, negative 2, 3, and negative 6. So I write those, 1, negative 2, 3, and negative 6. We want to evaluate f of x when x equals to negative 1, so I write negative 1 in the upper left-hand side of the table. I now carry down the leading coefficient to the bottom of the table, and now we can get started. We have 1 times negative 1, which equals to negative 1. I now add this negative 1 to the negative 2 above it. That's negative 2 plus negative 1, which equals to negative 3. Now negative 3 times negative 1, which equals to 3, and I now add this 3 to the 3 directly above it. So that's 3 plus 3, which equals to 6. I now multiply 6 by negative 1, so 6 times negative 1 is negative 6, and I add this negative 6 to the negative 6 above it. That's negative 6 plus negative 6, which is negative 12. So this negative 12 tells us that f of negative 1 is equal to negative 12, and what's important here is that it's not equal to 0. So negative 1 is not one of this polynomial's zeros. So we move on and we try other factors in this list. But for the sake of saving time in this tutorial, I'm not going to try all of these out. I'm going to go straight to one of the values that I know is a 0. So I'll go ahead and try x equals to 2. So let's calculate f of 2. Again, I use Horner's method, which I present in a table, looking like this. And at the top of this table, I write the coefficients of f of x again. So those were 1, negative 2, 3, and negative 6. I'm evaluating f of x when x equals to 2, so I write 2 on the upper left-hand side of the table, and I now carry down the 1 to the bottom of this table here, like so, and now we can get started. So 1 times 2 equals to 2. I now add this 2 to the negative 2 above it. That's negative 2 plus 2, which equals to 0. I now multiply 0 by 2, which equals to 0, and I now add 0 to the 3 above it. So that's 3 plus 0, which equals to 3. I now multiply 3 by 2, that's 2 times 3, which is equal to 6. And finally, I add this 6 to the negative 6 above it. So that's negative 6 plus 6, which equals to 0. Now, the fact that this equals to 0 tells us that f of 2 equals to 0. In turn, this means that 2 is one of the zeros of this polynomial. The factor theorem therefore allows us to state that because f of 2 equals to 0, this implies that the linear x minus 2 is a factor of f of x. So we can go ahead and rewrite f of x as follows. F of x equals to x minus 2 times some other polynomial. Now that other polynomial, luckily for us, can be found simply by reading the coefficients that I'm currently underlining in green. This will be a quadratic polynomial since f of x was a cubic, and its coefficients are 1, 0, 3. And we call this polynomial the quotient polynomial, capital Q of x, which equals to 1x squared, so that's x squared, plus 0x, so I don't write that, plus 3. So going back to f of x, I can now write f of x equals to x minus 2 times x squared plus 3. Now to finish factoring f of x, we need to go ahead and write this quadratic x squared plus 3 in its factored form. In other words, we need to try and factor x squared plus 3. But if we're working within the set of real numbers, then the equation x squared plus 3 equals to 0 doesn't have any real solutions. Indeed, you can go ahead and try, but solving x squared plus 3 equals to 0 leads to x squared equals to negative 3, which doesn't have any real solutions. So we cannot factor this cubic polynomial any further. And so the answer to question 1 would be the expression we have here. In other words, within the set of real numbers, f of x written in factored form is f of x equals to x minus 2 times x squared plus 3. And that's the answer. Now, if you're familiar with complex numbers, then yes, indeed, we would be able to factor this further. But we'll be learning about that further on in this course. And we now move on to question 2, in which we were asked to solve f of x equals to 0. Now, in this case, to answer question 2, since f of x has now been factored, we can state that f of x will equal to 0 if x minus 2 equals to 0, or if x squared plus 3 equals to 0. This first equation leads to x equals to 2, and this second equation leads to x squared equals to negative 3, which doesn't have any real solutions. So the only real solution that this equation has is x equals to 2. And that's the final answer.